Hey, Assalamu alaikum students, myself Irfan and you are watching Irfan Sir's Academy. Today we will discuss the topic that's what is the magnetic field surrounding a thin straight conductor. In order to find the magnetic field due to thin straight conductor, we will use here BIOT-SAVART law, the very basic law which we will use here to find the magnetic field at any point surrounding this long straight thin conductor. Now you know that Coulomb's law is a basic law which can be used further used to find the value of the electric field of different types of configurations. Here we will use BIOT-SAVART's law. If you don't know about the BIOT-SAVART's law, if you don't understand the BIOT-SAVART's law, the link is given in the description box and you can check out there, and after that you can find this topic very easy. Now in order to find the magnetic field, suppose we have a conductor. Let us suppose we have a conductor. AB is a conductor. AB, it's a long straight conductor whose length is AB. We'll first assume it has some finite length. Then after that we will use it has some infinite length. For that we'll use some special cases there. AB, it's a long straight conductor, and P is some point here. P is some point which is at a perpendicular distance. Suppose it is R. Suppose it's a perpendicular distance of R from this long straight conductor. Here it's a point P. Now in order to find this magnetic field at this point, we'll first calculate what is the magnetic field due to this small current element. What is small current element? A current element is nothing, a small element of the conductor whose direction is in a direction of the current. Suppose I is a current flowing in a direction from B to A, or in a y-axis direction. From B to A, we assume this is a y-axis, and this horizontal, it's an x-axis. Horizontal line is x-axis, vertical line, it's a y-axis. From B to A, the direction of current is from B to A, means from downwards to upwards. And the direction of the current element will be also from downwards to upwards. Suppose a current element, I have a current element, small current element. Suppose that current element, it is dy. It has a length of dy, and this current element, it is at a distance of y from this baseline. The perpendicular distance we take, that is r, and from that point, suppose this point is O. From O point, this current element, it is at a distance of y units. And the length of this current element, it is dy, very small, and dy, it approaches to 0, very small. It approaches to 0. That's why we take infinitesimal current element. It is an infinitesimal. Infinitesimal means here it's very small. It approaches to 0. Now suppose the position vector of this current element from this point P. The position vector of this current element from this point P, it is r, small r. If we write a vector, that will be r. We write an arrow. Arrow means here it's a vector. Suppose it makes an angle phi with the horizontal. It makes an angle phi with the horizontal. If this angle, what will be this angle? This will be 90 degree. And what will be this angle? This angle, let it suppose this is angle theta, and you will say that this theta, it's equal to 90 minus phi. 90 degree minus phi. Now suppose the elevations of this point, the elevations of this point and this point, suppose this is, it has an elevation of alpha and it has an elevation of beta. Here we assume that upward angle in clockwise, we will assume here it will be a positive angle, and in anti-clockwise or counterclockwise direction, it will be a negative angle. But we know that in counterclockwise direction, the value of the angle, it is assumed to be positive, and in clockwise direction, it is assumed to be as negative. But here we will assume that in clockwise direction, it will be positive, and in counterclockwise direction, it will be negative. There will be no difference in the answer will be same. Hope you understand that. Now suppose alpha is the elevation of this point, the one end of this long straight conductor, and beta is another elevation of this end, that's end B. which makes an angle beta with the horizontal. We know that this dy, it is a small current element. Dy, it's a small current element. Small element, if you write I dy, it will be small current element. Small current element. Now what is the direction of the current element? It will be in a direction of the current. Current is in this direction, the current element, the direction of the current element, it will be in a direction from B to A. Now we know that theta, it will be equal to 90 minus 5. 90 degree minus 5. Now what is the magnetic field due to this small current element? We know that this magnetic field due to this small current element dB, it's equal to mu naught upon 4 pi, where mu naught is the magnetic permeability. IDL, I is the current flowing through the conductor and also through this current element. IDL, this current element, sine of the angle which this current element makes with the position vector. What position vector? The position vector is from the current element to the point where you have to find the magnetic field. The position vector is R, and this current element, it makes an angle theta. It will write IDL sine of theta. Now here the value of current element is the length of current element, it is dy. Instead of dl, we write here dy upon what is the distance between the two, that's r square. So magnitude of the magnetic field. Now we have to find, first of all, unknown things are, we have the known things, that's this alpha. The another known thing, we have beta. Alpha we know, beta we know. We don't know about this theta. In order to find theta in terms of alpha and beta, what we will use here? We will use here some basic geometrical laws. First of all, you know that what will be here? Sine of theta. Suppose this is an equation number first. Now here we will find the value of this y. In order to find the value of y, we will use here basic geometrical rules. One is tan of phi. What will be the value of tan of phi? The tangent of phi, it will be perpendicular upon base. Perpendicular is y upon base, that's r. Which further implies that y will be equal to r tan of phi. Now differentiating both sides with respect to phi, it will be dy upon d phi. It will be equal to r. What is the derivative of this tan of phi? It will be sec square phi. Sec square phi. Now you will find the value of dy. The value of dy, it will be r sec square phi d phi. This is the value of the value of dy. Now the another unknown thing that's here, that's r. We know the theta is 90 degree minus phi. We know only the value of phi. We don't know about the value of theta. We know the value of phi. If you know what is the value of r, we can find here from this triangle. This r we know, this capital R we know. We can find here this hypotenuse, and here it is base. Hypotenuse upon base, that will be sec of phi. What is sec of phi? Sec of phi is equal to hypotenuse, that's r upon capital R base, and r, it will be equal to small r, it will be equal to capital R into sec of phi. Very easy. Now what are the unknown things? One is r, we find this. One is dy, we find that. Another one, that's theta, we find that. Now put the values, we will get the answer. What will be the answer? The answer will be b db, it will be equal to mu naught upon 4 pi. It will be I. What is the value of dy? It's r sec square phi d phi. Int, what's the value of sine of, what is theta? It's 90 degree minus phi upon, can you tell me what is the value of, what's the value of r? The value of r is, it is r square sec square phi. If you see that, this will be, this is dy, the value of dy. This is sec square phi, it will go, and this is r, and 1r, it will go sine of 90 minus sine of 90 degree minus theta, it will be equal to, it will be cos of theta, and here it is phi, it will be cos of phi. So you write here what's the value of this. Now what will be the value of dB? The value of dB, it will be equal to mu naught upon 4 pi, it will be I upon capital R, I upon capital R, it will be cos of phi. Now it's the value of the magnetic field due to small current element. It's the value of magnetic field due to small current element. Now in order to find what is the value of the magnetic field due to the long straight thin conductor, we will integrate this throughout the conductor. Why will we integrate? Because the conductor is a continuous. Whenever we have continuous bodies or continuous systems, we'll use their integration. Where we have something discontinuous systems, then to add up all the elements, we'll use their summation. But here it's a continuous system, we'll use here integration. But it will be the magnetic field due to a whole conductor, it will be integration. Mu naught upon 4 pi, it will be I upon capital R, it will be cos of phi. And what will be the limits? Yeah, the limits of will be phi will vary, and this phi will vary from alpha upon beta. And we tell earlier, we will take clockwise direction as positive and anti-clockwise direction as negative. We will assume there, and it will, the values will be, it will be phi will vary from minus beta to phi will vary from alpha. Now what will be the integral? We'll solve this into mu naught upon 4 pi is a constant, I is a constant, R, capital R is a constant. What's the integration of cos phi? It is obviously sine of phi. And limits will be minus beta to alpha. Now we will solve this. Mu naught upon 4 pi I upon R. It will be upper limit sine of alpha minus lower limit sine of minus beta. And the value will be, what will be the value? We'll put here. The value will be, the value of B due to whole conductor, it will be mu naught upon 4 pi I upon capital R, it will be sine of alpha. What's sine of minus theta? It's sine theta, not sine theta, it's minus sine theta. You know that sine of minus phi, it will be equal to minus sine of phi. I hope you know the quadrant chaining in case of trigonometry. Now it will be minus sine of beta, minus into minus will be plus, it will be sine of beta. This is the magnetic field due to a thin straight conductor of some length, and it will depends on what factors. It depends upon alpha, it depends upon beta, it depends upon the perpendicular distance, and it depends upon the current. No doubt what is the length, of this conductor, it's independent of the length of the conductor. It means if you have the same values of alpha, beta, r, I, same values, alpha, beta, r and I, no doubt you will not be able to find the same values of alpha and beta, because when you increase the length of the conductor, the value of alpha and beta will get increased. Now ultimately, if you find for infinite long straight conductor, what will be the value of magnetic field? You know that for long straight conductor, what will be the value of alpha? It will approach, it will increase, it will go increase, ultimately it will become 90 degree. It will be 90 degree. And what will be the value of beta? Same here, it will be 90 degree. Therefore, what will be the value of B? It will be mu naught upon 4 pi into I upon R into, what's the value of sine 90 degree? It will be 1. Sine 90 degree, it will be 1. It will be 2 here, 2 1 R, 2 R. It will be mu naught into I upon 2 pi R. This is the value of the magnetic field due to an infinite long state conductor. What is the value of magnetic field surrounding the infinite long state conductor? The value is mu naught upon 2 pi I upon r. What's r? It's perpendicular distance of the point where you have to find the magnetic field from the long state infinite conductor. What's I is the current flowing through this conductor and depends only on these two parameters. For any type of conductor, it depends also on these inclinations. What are the inclinations? One is alpha, one is beta. For infinite long state conductor, it approaches to 90 degree, this inclination, and putting the value of alpha and beta equal to 90 degree, you get the answer for infinite long state conductor. I hope you understand this. Okay. Now, what will be the direction? The direction, who gives the direction? You know that Maxwell's screw rule, or you can find by right hand thumb rule. How can you find this direction? The direction of this B, this direction of this magnetic field B, direction is given by, the direction, it can be given by right hand thumb rule. Right hand thumb rule. And what right hand thumb rule tells us? Right hand thumb rule tells us that if you imagine a conductor in your right hand. I imagine a conductor, suppose a pen, it's a conductor. I imagine this conductor in my hand. You imagine this conductor in your hand, right hand, not in left hand, right hand. Suppose this thumb, it points in the direction of the current through the conductor, like this. Suppose this thumb, it points in the direction of the, current. It points in the direction of the current through the conductor, this thumb. Then the curling of your fingers, what will be the curl of your fingers? The curl of your fingers, it will give you the direction of the magnetic field. If you will tell me there, what will be the direction of magnetic field here? If the current, it will be, if the current through the conductor, it's from B to A, and point P lies from the right side. What will be the direction? The current, it is in this direction. What will be the direction? It will be counterclockwise. It will be like this, counterclockwise. Suppose if we have to find the direction like this, current is approaching from A point to B point, what will be the direction? It will be, the current, it is in this direction. The curve will be, it will be clockwise. Isn't it? I hope you understand the direction of the magnetic field due to this long straight thin conductor. For infinite also, the direction is also the same. Now, what will be the graph of this magnetic field? If you will see here, for a constant value of current, for infinite long state conductor, we are dealing here with long infinite state conductor. If you draw the graph here, what will be that? This B, it depends inversely upon R for the constant value of current. If the current is constant, what will be the value of B? It will be inversely proportional to the value of R. What's R? It's a perpendicular distance of the point P from the conductor. If this point P is at a large distance, more is the value of this R, less will be the magnetic field. And within that, you will go far away from the conductor, the value of magnetic field, it will go on decreasing. And the graph, it will be, yes, it is rectangular hyperbola. It is P and it is the distance. The graph is rectangular hyperbola. Okay, this is what's the magnetic field surrounding a thin straight conductor. I hope you understand today's session. If you like our lecture, then subscribe our channel, like our channel, and do share our channel. Okay? And also tap on the bell icon so that you will be able to find the notifications of the upcoming lectures. I hope you understand. Thank you.